Anyhow, what I was saying is I've also been working as editor on a e-zine on art, poetry, and politics, focusing on anti-racism at breatheeveryone.net. We've been going for about 5 months since the George Floyd murder. The October issue just came out today. So if you're interested, you can go look at that afterwards. The other thing on the opening slide here, I put in a new lead speaker, Hongjing Liu, who's actually the lead person on all the theoretical work I'll talk about. She couldn't present because she's about to start teaching, because also today is the beginning of spring quarter at UCLA. So what I hope to do is to give you kind of an overview about what we call the BART project, Bayesian analogy with relational transformations. Hongjing and I, with various collaborators, have been working on it for most of a decade now, basically trying to learn semantic relations from non-relational inputs generated by machine learning. This is Hongjing and also Yingyang Wu, who was a statistician who's a co-author in one of our recent papers. So general roadmap for the talk is I'll spend some time just introducing like what our goals are and why we have those goals, and then talk a bit about the model, and then how it gets applied to a bunch of empirical phenomena in relation, typicality and similarity, how we get from relations to analogy, how we try to find relations in the brain based on the theoretical work, and finally how we get from analogy to mapping. I should say I'm kind of assuming that this is a relatively sophisticated analogy audience, and I'm going to go over some things sort of just by assuming common background, which may in some cases not quite work, but we'll try. So I like to start these days with a quote from the British Romantic poet Samuel Taylor Coleridge back a couple of centuries back. The creative mind needs to become accustomed to contemplate not things only, but likewise and chiefly the relations of things, which kind of captures, of course, the importance of relations and its connection to creativity. And as you can also see at the bottom of the slide, I partly use this as an excuse to gratuitously refer to a book I wrote that came out from MIT Press last year, The Spider's Thread, Metaphor in Mind, Brain, and Poetry, because some of you may know my other general interest is in poetry. And Coleridge is an interesting figure because he had a theory of imagination, which was kind of a proto-psychological theory long before psychology in its modern sense was invented. Another quote I'll toss up to kind of go along with that is from Adrian de Groot, 1946. As many of you know, he was a Dutch psychologist who did the earliest work on expertise in chess, preceding the famous work of Chase and Simon. As always, when we talk about seeing in chess, it's the perception of the relations between the visible objects and not the perception of the objects, boards and pieces themselves. So whether we're talking about language, like Coleridge, or perception as de Groot, both put great emphasis on relations. And in some of our work, in fact, we're working on visual perceptual analogies, although today I'm going to leave that aside and just focus on semantic concepts. So what's a relation? So there's a formal definition. Here I'm adapting it as stated by Graham Halford, but it actually comes from logicians. A relation corresponds to an ordered set, and for present day purposes, I'm only going to focus on ordered pairs or binary relations. So for example, larger of xy is true for various instantiations of it that make it so. Dog, mouse, elephant, lion, bear, goat, etc., etc. So when I talk about relation learning today, what I basically mean is acquiring some knowledge structure that has the properties laid out here. And notice relation, as I'm centrally using it, refers to the entire structure, like larger xy, not just to the verbal expression larger. There's often a tendency to think of relations as verbs and prepositions and other similar kind of linking expressions, and that's true. But you can have a relation that doesn't have a common linking expression at all. And in fact, as you'll see, in some ways, most of what I'm going to be talking about today is sort of an analogy without the verbs and the linking expressions. Also, each entity plays a particular role in the relation. So dog is the larger one, mouse is the smaller one. That leads to an important property that you can take any binary relation and create its converse, which flips the role assignments. So larger dog mouse is equivalent to smaller mouse dog. So in fact, that's going to be a very useful technique for creating relations quickly by essentially allowing the converse of any relation to be introduced. And then the final sort of point is sometimes when we're talking about the relation between a pair of words like dog mouse, and notice that's not one single relation. So it's true that dog mouse instantiates larger, but it's also true that the dog is less wild than the mouse, that both are mammals, et cetera, et cetera. So to various degrees, two words may be linked by many relations. And when I talk ultimately about a distributed representation of relations, that's basically what it looks like, an array of alternative relations that are filled to some degree by that particular pair. When we get into the empirical stuff, there's some basic phenomena that any model of relation needs to explain. Relation typicality, not all relations are equally good examples of a relation. Relation similarity, it's graded, that like, you know, hot and cold are opposites and are very different than, say, similar pairs. Friend and enemy are opposites, but they also have some more similarities as well. So the two kinds of opposites won't actually be exactly the same in a similarity space. I'll go into this more carefully as we go. And of course, as I just mentioned, it's possible to form converses and probably, of course, other operations that depend on the systematic properties of roles. And kind of the psychological issue is sort of how do you at the same time get these kind of graded phenomena like typicality and similarity, but also get these sort of like more obviously symbolic properties that depend on role identities. Now, I'm sure everyone here knows that analogy, analogical mapping, is clearly interdependent with relational representations. Here's kind of a standard structural mapping style representation of the analogy between the solar system and the atom. And all I sort of want to point out here is that obviously it's kind of organized among shared relations across the two domains. So this being the source is kind of the richer one, the knowledge about the planets, and we're going to use that ultimately to figure out some new stuff about the atom. And in doing that, there's a lot of emphasis on forming mappings. The planet corresponds to the electron and the sun to the nucleus, etc. So an analogy is obviously bound up with mapping. So to be careful here, when I refer to mapping, I mean something like this, where because of the interactions among multiple relations, I'm able to draw the inference that certain objects or concepts play comparable roles. And that's going to be important for inference, so I can make up new inferences about electrons by adding stuff that I carry over from my knowledge about planets. So this representation is obviously a symbolic network style. It's kind of it's one of many such representations that roughly flow from Collins and Quillian, 1969, their theory of conceptual hierarchies. Similar things fed into the Eleanor Project in the 70s, and then human associative memory with Anderson and Bauer, and then John Anderson's ACT model. I was, in fact, as I was just thinking about this, I was realizing when I was in graduate school, I was working on network models kind of in the Collins and Quillian vein. And this is one of the, apparently many times when over the course of 4 or 5 decades, I changed my mind. At the time, I thought network models were the natural way to go. They went up against feature comparison models. So it's kind of roughly, how do you know how a robin is a bird? Is it because you find a link in memory? That would be the network style. Or is it because you do some sort of calculation based on the features of robin being compared to the features of bird? That was Rip, Chauvin, and Smith and others. I entered in on the side of the former, the Collins and Quillian style. And I would say by the 80s, 90s for sure, that had been thoroughly defeated by the more calculation on the basis of features style. Now, one issue that comes up, of course, is that, you know, how do you actually match up your relations? So more massive than, more massive than. What if they're not really identical exactly? Like one says bigger than. So in the network style, you basically, you know, look up superordinates and synonyms in some table, and you can make appropriate substitutions. In work I did with John Hummel, we developed a Lisa model, which was basically trying to combine connectionist ideas with structured representation. So in a sense, although this is kind of complicated, and it's kind of just showing the dynamics of what's active when as you go through some mental processing. But basically, it's trying to translate propositional style structures very similar to what we saw in SME into something that has a neural basis. And sort of pull out what's this and this. This is some units firing, and they stand for the roles of a verb. I think it supports. Pulling them out, this is just showing that they're oscillating, which is kind of how Lisa does role binding. But notice basically that we have some features for the first role and features for the second role, and those collectively represent the relation. So this is, in fact, a kind of very role-based formulation where the relation really is the roles that make it up. And furthermore, the relational stuff is the same kind of stuff as objects. These are like a person who's a particular person is oscillating, and they're a disjoint pool of units, but they're both semantic units of the same general sort. So that's kind of where analogy models have tended to be. But now I want to sort of motivate why we kind of have gone to some other issues that I think have been relatively neglected. I'll call these the 3 buts, because I got three issues. First of all, do these analogy models really in any interesting sense understand relations? So one could argue that they're basically static representations, like here's the representation of this relation, but that doesn't allow the model a way to basically determine autonomously whether the relation actually holds or not. So it would seem odd, for example, to say, well, I'm a good English speaker and I know what hot means and cold means, and I know what an opposite is for sure. Yet, regrettably, I don't actually know whether hot is the opposite of cold. That seems just odd, because that's kind of what it means to know what an opposite is to be able to decide whether hot and cold are or aren't. So part of what I want to argue is that if you want a relational representation that's more realistic, it has to, at least in part, be a function that will take an input and return a truth value. Or if we go into the land of probabilities, let it be a probability of something being true. The second but is, well, what about proportional analogies? The familiar ones from SAT tests and the like, A is to B as C is to D, like hot is to cold as love is to hate. Again, this is kind of a interesting sort of twist in my own, I guess, career fate, because many of you probably know it. Back around 1980, I was working with my student Mary Jick, and we developed, did some work on analogical problem solving with Dunker's radiation problem and analogs to it. And I recall very clearly that in part we were reacting against the work that Bob Sternberg and others had been doing on proportional analogies, which seemed to us kind of dull and beside the point. And I knew that pretty well because actually Bob was in the office next to me in Stanford when we were in graduate school together, and I more or less ignored what he was doing. So we decided to just get away from them. But it's always kind of bothered me that we have all these fancy models with other relations and mapping, but it isn't exactly obvious how, in fact, they even apply to the proportional analogies. So in particular, the relations here are not in the input. They're just not there. You got to figure them out. In fact, Charles Spearman, who started modern work on intelligence about a century ago, called the first step of analogy the induction of relations, which is figuring out what the relation is, followed by what he called the induction of correlates, which is trying to figure out how does that relation relate to the CD relation over here. And also, you know, people will casually say, well, you're mapping AB to CD. Taken more seriously, you know, the mapping here is completely trivial. I don't have to compute the mapping. It tells me A is C and B is D, and that's it. But moreover, that doesn't tell me anything useful about whether the analogy is actually valid. So I could put hot is to cold as alias is to name. Terrible analogy, but A is C and B is D. So something else must be going on. And then finally, the one I want to focus on the most is, well, where do relations come from? We analogy theorists, on the one hand, think of relations as central to analogy. On the other hand, have kind of largely taken them for granted in the sense that it's, the theories don't really tell how they're learned in the first place. And I must say, as one of those who have taken that approach for a long time, I don't think we can be faulted in any deep way because it's a very hard problem and you got to start somewhere. So we started by assuming the relations and moving on. But suppose you're trying to address the question, where do relations come from? There's several possibilities. First of all, maybe they don't come at all. And in fact, if you look at current work in artificial intelligence and deep learning, actually probably the bulk of current computational work on analogy is doing away with relations so you can solve human-like tasks that seem pretty complex, like translation between languages and other natural language processing without relations at all. But I'll set that aside for today. Maybe some or all of the relations are innate. Them all being innate seems a bit of a stretch, but it's possible there's sort of core relations that are innate and we work from there, but someone would have to work out the theory. Probably an interesting possibility is that relations might be acquired from sort of more elementary relational features, which we'll never really propose as a learning model is plausible. Roger Chaffin and Doug Herman back in the 80s did some nice work, somewhat neglected, I think, going over with semantic analyses of relations. And these are things like, well, are they symmetrical or not symmetrical? If you're in the domain of part whole, are we talking about articulated objects or mass quantities? So, you know, probably 20 or 30 relations like that are potentially interesting building blocks. But I'm going to set that aside for today too. In cognitive science, I think the first really serious effort to learn relation from non-relation inputs was the DORA project that Alex Dumas and his collaborators did, which essentially was trying to extend the LISA model by learning the relations that go into them. The DORA stands for the discovery of relations by analogy. And in a nutshell, the idea is you take and so at least some elementary style analogical mapping, and use that to kind of bootstrap up relations. And finally, the approach I'm going to focus on now, BART, is trying to learn from non-relational inputs using more basic computations. In fact, you know, there's a sense in which BART is the opposite of Dora. And Dora is learning relations by analogy. BART is going to try to extract analogy from relations. So we're not going to assume that you start with all the fancy mapping apparatus all ready to go. Rather, that's going to be kind of a late development. So here's the central ideas for the project. I'm going to try to learn relations from non-relational inputs. And furthermore, as we'll get into, these are going to be non-relational inputs that we, the experimenters, didn't make up. Because you know, it kind of feels better to sort of keep yourself honest if you try to work from inputs that were not hand-coded by anybody, and especially not by you, the modeler, because it's all too easy to sort of like assume, well, you know, wouldn't it be great if we had common features in these two things and we could kind of intersect them and find those common features. And in order to ensure that that's true, you build representations with those common features, but maybe they aren't there in the human brain. The focus is on assessing differences between entities, and differences we'll see I really mean pretty much mathematical differences, like subtractions between quantities. Roughly, it has the approach of smart learning built upon deep learning, is that we're actually going to use the products of deep learning from massive amounts of data, text corpora in particular, as the inputs, and then we're going to have, you know, the so-called smart learning, which will take a small number of further examples that are focused on specific relations and learn something from them. And what it's learning basically is successive re-representations so that the relations become increasingly explicit. And then analogy emerges as simply the ability to assess the similarity of relations. And ultimately, mapping, a late development, is based on the ability to assess the similarity of patterns of relations. So I'll try and unpack that as we go on. So for the rest of this talk, when I'm referring to non-relational inputs that were not created by us, the experimenters, I mean word embeddings derived by the Word-to-Vec model of Tomas Mikolov and others, then at Google, later Facebook. These are basically densely distributed semantic representations of word meanings extracted by processing, essentially, you know, trying to use words to predict their neighbors in text for extremely large text corpora. Everything we do is basically Google News, 100 billion or whatever text by now. So you don't need to understand this, of course, in any detail. In fact, sort of the fact that you can't understand it in any detail is sort of the point. These are actually fragments of the representations for various animals. Typically, we work with vectors that are with 300 dimensions. Each dimension is not like an on or off feature, it's a continuous value from negative to positive, which is what the grayscale is indicating. And all the words are represented on those same 300 dimensions. So the first thing to notice, of course, is that I, at least, haven't the slightest idea what any one of those dimensions is. They look like kind of a blur, but actually, I've actually organized these animals large to small, rhino at the top, working our way down to weasel at the bottom. One of the earliest things we've done is simply learn the relation larger than, and it can do that very well, and then make larger than judgments about brand new animals that it hasn't seen before. I find it even now very challenging to look at this and say, well, how come the rhino is large and the weasel is small? But statistically, there's a reason buried in there. One of the reasons Word-to-Vec particularly got attention is because it itself turns out to be able to solve some proportional analogies. Probably the most famous analogy in all of artificial intelligence today is king is to queen as man is to woman, which falls out of the model. And the way it, quote, falls out is, as illustrated here, this is reduced to 2D space for visibility, the vector that one would draw between man and woman runs parallel to that between king and queen, which is to say cosine distance of 0 between those vectors. So that parallelism is sort of the definition. So, so over on the right, another semantic one, like Germany has capital Berlin, Paris, so France has Paris, and over there up above we got China with Beijing. Notice that although they're distributed through space, there's kind of the same downward slope between the two of them. Now this was 2013, and by now Word2Vec is kind of old hat. It's well known that despite these kind of interesting successes, you can easily show that it can fail pretty on more challenging problems. Here's an analogy from Adam Green. Blindness is to sight as poverty is to, and probably the answer would be money or wealth. Here's the top 20 choices that come out of the Word2Vec algorithm. Poverty to poverty seems a little dumb. Breadline sight, impoverished, poverty again, poorest, destitution. Basically, none of them make the slightest sense. The only one that's vaguely in the ballpark is incomes, which is down the list the way, but basically pretty much of a miss. But a couple of things to say though in favor of Word2Vec and the like. First of all, Word2Vec itself is so 2013. These days, Mikolov himself has moved on to fast text. There's a system called BART, vastly more famous than our BART, which is probably better for a lot of things. We in fact haven't seriously used them yet because Word2Vec sort of works good enough, but you could do better in principle. Also, you got to remember, Word2Vec wasn't an analogy model. It was just a model based on learning how to predict neighbors in text. So it's kind of just serendipitous that, in fact, it can start to solve some simple analogies as well. And one of the things that seems to be kind of a nice idea is, in fact, that you focus on the differences between two things. And if there's a limitation to this approach, what I would say it's like a limitation of distance models in general. By themselves, they have no way to, they have one generic representation of meaning as points in a multidimensional space. But what you would like to do is kind of reweight that space for different relations to capture the fine-grained variety of specific relations. And that's kind of what we're going to try to do. Okay, so let's sort of get into it. So there's going to be some challenges. The most obvious one is that how are you going to learn anything from these highly distributed representations where you can't even find like size as a feature, at least on the face of it? And then there's another problem in analogy. How do you figure out alignments that don't seem to involve the same attributes at all? So love is the opposite of hate, and that's got something to do with emotion. Rich is the opposite of poor, and that's got something to do with wealth. But how are we going to match up the emotion information from one with the wealth information in the other, when at this moment, we're, by a definition, we don't have relations yet, so how do we get started? Okay, so in everything pretty much that I'm going to say going forward, we're going to work with some materials that come out of a set of norms of abstract semantic relations. Because in order to do anything, we got to get the model to get started. We need some relations to train on and then test on. So this is a project I did some years ago with David Jurgens, Saeed Mohammed, and Peter Turney, David was a grad student in computer science at UCLA. Saeed and Peter are AI guys in Toronto. And we did a project for the Semantic Evaluation Conference, which is a natural language processing conference. So working from an earlier taxonomy that linguists and psychologists have put together, we took 79 semantic relations that occur often in analogy problems and in language in general. And for each of them, we acquired a bunch of m-turt data to generate a rank order based on their prototypicality. So this is what we ended up with. The relations have 10 general types: category, part, whole, similar, contrast, etc. And those types have different subtypes such that there's a total of 79 subtypes. And we did this exercise for each one of the subtypes, giving us in the end on the order of 3,000 plus word pairs that were ordered into subtypes. Well, we'll go through all those examples now. Here are actual examples for 4 of the subtypes, ordered by prototypicality, which based on human ratings. So house, home is an excellent example of a synonym. Clean, tidy isn't so good, although it's sort of a synonym too. Hot, cold is an excellent contrary. Warm, cool, not so good, etc. So the original challenge that we actually did our thing as essentially an AI challenge. AI people love to have challenges to solve. People had to have models to kind of predict the ordering. And it's become a bit of a cult project in the years since, actually. The original models all totally failed. But as we'll see, things like Word2Vec have actually done rather better. So let me tell you about the BART model after this long-winded preamble. We're going to try to deal with the densely distributed representation using some sort of fancy statistical methods for dimension reduction with priors. And we're going to try and solve this alignment problem using difference-ranked features. So let me explain that point first, because it's sort of before we get into the broader model. Roughly, here's what we're going to do. I give you an example of, let's say, opposite, like cold and hot. Each of those is a vector of 300 that we draw out of Word2Vec. Here, of course, greatly simplified. I line them up, and I can take the difference between those vectors, and I get something like this. So, for example, this obvious bright spot is the difference between, I guess it's that dark spot, no, this light spot and this dark spot. So it's a very big difference. So that's why it's white. Having done that, I can order them in order of distances, here least to most. And then having done that, I can kind of line those new differences up along with the original set I started from. So, roughly the idea is that if a certain dimension plays a certain kind of functional role for one pair, let's say it's the one that has the largest difference, say for opposite, then another pair might also have a dimension which has its largest difference. There's a good chance that those two dimensions are playing kind of similar functional roles for those two pairs, even though they're different dimensions. So we're now going to rearrange the values so that your largest difference for one pair is actually lined up with the largest difference for the other pair, setting aside the original identities of those dimensions. So here's the BART model itself. Now, there's a lot of fancy math, and I'm not the one to explain it, and we wouldn't have time anyhow, but let me sort of step through it. Let's imagine we're taking examples of opposite, the relation we're trying to learn, such as love and hate. We get an input vector for each one, which we pull out of Word2Vec, 300 long. So we get they're concatenated, we got 600 dimensions. Then we take them and we do that difference operation and reordering. and take the result and move it back to the level of the individual features. So we don't throw away what we started with. Oh, I should say, if you don't think of this as like a standard neural network that's feed forward from bottom to top. It's more like a recipe for constructing a network. So we take this, and here it is still again, and this here still again. But over beside it now, I've got the reordered features of this pair for love and for hate. So now I've actually got 1,200 features. So at the next level, we apply statistical methods for reduction of the size, essentially using regression methods, elastic net regression, to try to drive as many dimensions as possible to zero weight, so that we end up with just a subset that seem to be the ones that are the most important for pushing forward. Then at this level, we apply the contrast priors. The model makes the entering assumption that the opposite weights have opposite signs for the two features. Notice, by the way, we kept the color coding. Everything that has to do with the first term is in red and the second term in blue, and that's still true when we get up to here. So what was 1,200 here is variable, but now it might be like 250 or so here. Finally, we do Bayesian logistic regression to come up with weights and, in fact, a full variance covariance matrix on these surviving dimensions to predict the posterior probability that the relation opposite holds. So that's it. Okay, this is where I thought I would stop for questions. I see I'm like way too slow, but Margarita, can you tell if anyone's got a question that's sort of worth throwing in at this point?
Yes, there is one question, which is, why do you need to retain the original order if all the information is retained in the reordered vectors?
Right, good question. The answer is because all the original information is not retained in the reordered vector. The reordered vector has created these contrasts based on kind of functional difference, but it's lost the stuff that word-to-vec initially offered, which is embedded in the original features. And in fact, if you look from relation to relation, the balance of original versus reordered features varies here, but it's often the case that there are more original features than there are reordered ones. And one thing to emphasize is, there's a million ways basically that BART and its like can fail. And the first way is that we didn't get some relevant information in our inputs. And we've worked on this for a decade. We started with latent semantic analysis, LSA. It's not very good. By 2012, we were using a topics model, which was better. If you use word-to-vec, it's, roughly speaking, 10% increment improvement just by changing the input. Basically, secretly, in a word-to-vec or similar embedding, you've got information about the form class of the word, noun or verb, and its abstraction level and things like that, which actually are highly relevant to relations. So in fact, we need to augment it, but we don't want to lose the original starting point either. Okay, I better press on, and then we'll come to whatever questions in the end. One last point, if you ask me at this moment, okay, what's the relation representation for opposite? The answer at this point is, well, it's the weight distribution on these right here. So notice, as I said, this isn't all preserved. In the end, what you walk away from after this learning, and I should say, I've given you one word. The model takes in all the positive and negative examples. Roughly speaking, we're usually training with about 20 positive examples and maybe triple that negative examples drawn from other relations. In the end, that's the relation representation that I'll be referring to as we go forward, but it's going to get further re-represented. Now, the first thing you can do with this is just see, well, does this predict relation typicality? Just making the assumption that for any word pair, the posterior probability that, for example, it says this is a class inclusion relation, does that map on to the ordering that we have in the Jurgens norms? This was one of the interesting things that Word2Vec itself did. It was getting correlations kind of roughly 0.3, which was actually about as good as any AI model had done at that point. BART gets correlations on the order of 0.8, which is pretty close to the split half reliability of the norms themselves, and therefore probably about the best that could be done. So that's kind of encouraging. The next step we took in the model was to return to the issue that I sort of flagged at the beginning. How do we represent the relation between a particular pair of words? Because what I've been talking about is how do you learn a particular relation, like opposite? But for a pair of words like love, hate, it has a probability of being an opposite. It has a probability of being a category member, probably low, etc. But for some pairs, actually, friend, enemy, for example, you're probably going to see some fairly positive probabilities for multiple relations. And another important point is if you look back to it, I sort of explained how we got one relation and we have this very distributed representation for this weight matrix. When I learn another relation, I set up another network. So the BART is sort of avoiding the issues of crosstalk where things blur each other because new learning clobbers the old learning by simply assuming I got independent networks functioning for every relation I learned. So armed with that, I can simply create a vector. There were originally 79 relations. So BART, with its having learned them for any word pair, can create a vector of 79 where now the elements are no longer Word2Vec features, they're probabilities of each of the 79 learned relations. And armed with those, I can do things like start to look at the similarity of words in spaces, in like category membership, similar and contrast. So not every contrast falls on top of all the others. They're kind of distributed because they have degrees of membership in the other categories at the same time. Now, some of you last spring, I guess, heard Ichien, who works with Hongjing and me. He had done an experiment extracting human similarities for various subcategories out of the Jurgens norms. In this experiment, it was similar, contrast, and cause purposes, each with 3 subtypes. There's a theoretical, what's called representational dissimilarity matrix, or RDM, which is kind of an interesting idea, which is this represents how dissimilar each type would be theoretically. So if you're in the same subtype to a first approximation, you're not very different, you're similar. If you're in the same category but different subtypes, you're kind of medium. And if you're off in a totally different category, you're low. Collecting human similarity data, you can compare actually the human RDM, which looks like this. You can kind of see sort of an approximation to that theoretical RDM. And here's what we derive from BART, which now can predict. This is its measure of the dissimilarity among all the word pairs in this experiment. And we can do the same thing for our sort of original Word2Vec, which is Word2Vec difference, where you take the difference. And another variant is Word2Vec concat, which is just concatenating literally the two Word2Vec things, the two words. And it's essentially, this is measuring word-to-word similarity between pairs. And basically, BART is reliable and the best predictor, and that's even true when you sort of statistically remove the variance that can be accounted for by individual word similarity. Nick did a second experiment, different materials, different categories. You can see the humans look a little different. This category is kind of well structured, the others not so much. But BART actually kind of picks up on that. This one's pretty clear, these not so much. And once again, in fact, it's the best of the 3 at predicting human similarities. Now, the same technique allows us to start to solve analogy problems, because for any word pair, we now have a distributed representation of 79. So I get it for AB, I get it for CD, I take the cosine distance as kind of a score of how similar are they. So this is taking one of Adam Green's analogies again. Blindness is to sight as deafness is to hearing, would be a fairly close analogy. And this is showing the degree of probabilities across the 79 for blindness sight. And I don't know whether you can tell by the eyeball test, but it sort of matches up approximately to sort of the dark light for deafness hearing. And if you go to a more remote analogy, blindness is to sight as poverty is to money, the one we looked at earlier where word-to-vec failed. It's not quite as good, but take my word for it, it kind of matches up to some significant degree. You take something unrelated analogically, wall paint, it doesn't match very well. So basically, relational similarity by this cosine score goes down from the near analogy to the far analogy, and then a big drop to something that's not an analogy at all. We created some simple verbal analogies of categories, like insect to bee as fishes to halibut, against a foil like fishes to water, also related, same C term, but wrong relation to match A, B. For categories, functions, opposites, synonyms. See how well both word-to-vec itself, the word-to-vec difference model, and BART do. You can see BART is more accurate. Human M-Turkers kind of fall around here, about 84%. So although it's a little uneven across types, that's not too far from the overall performance of BART. So the next sort of general thing we did is ask the question, can we find distributed representations of semantic relations in the brain? This is the work done by Jeff Chang, who's right here, Yujia Peng, who's right there, Hongjing, Martin Monti, who's the senior author, our colleague here, and me. This was the graduation of both Yujia and Jeff a year and a half ago or so. In brief, and I'll make it brief because we're coming to the end. In the last 20 years, as many of you know, there's been a lot of work on how analogy problems relate to brain functioning. And Sylvia Bunga and Adam Green and many others have contributed heavily to this. And for present purposes, I just want to cartoon level summarize like where to look for analogy. Most attention has gone onto the rostrolateral PFC. All of this is typically left lateralized, which seems to be involved in kind of the final stage of analogical comparison or relation integration. Dorsolateral PFC seems to be involved in maintaining the relations. Ventrolateral seems to be particularly important for controlling interference, so driving down irrelevant associations that compete with the analogical one. And then importantly, Sylvia Bunga and Carter Wendelken and others have got evidence that actually the initial relation representation depends to a large extent on actually posterior or parietal cortex, which feeds into the network. So roughly formed here and then kind of moved forward or connected to frontal networks for processing. So we did an fMRI study. We took similar contrast and cause purpose, 3 subtypes of each, create a bunch of analogies of AV as a CD, high-low as up down, with invalid ones created by rearranging the pairs. So they're always related, but it's the mismatching relation. We did it sequentially like this. For 2 seconds, you see AB, rich, poor. Now this is very useful because that means the brain signal right here is kind of picking up primarily what you're doing when you're trying to represent the AB relation, because you can't solve anything yet. You don't know what you're comparing it to. Then you have a jittered interval, and then CD pops up, hot, cold. Now, of course, you can represent it, and importantly, you can actually do the relational comparison. Then you get a signal as to which button means yes versus no. So importantly, we remove kind of motor planning at this moment because you don't know which button. You can decide the answer, but you don't know which button you're going to have to press afterwards. Then we did a lot of analyses, but I'll just quickly tell you what you can do with representational similarity analysis. It's the same analysis that Nick Ichien was using in the semantic similarity judgments I just talked about. The basic, starting over here, the basic idea now is that if I give you two word pairs like rich, poor, hot, cold, and if they're kind of similar relationally, and that's what you're thinking about, then somewheres in the brain, there's going to be a similar neural signal. Rich, poor will be activated sort of like hot, cold. And from that, I can get a neural representational dissimilarity matrix. Then I can take any model I like that claims to be predicting how similar is rich, poor to hot, cold. So I can do it BART style. I can do the classic word-to-vec difference model, and I can do the kind of totally word-oriented word-to-vec concat. And now I simply compare these RDMs against the neural one. And what we find, well, those are the RDMs from the three models. You can see they're pretty different. If we look at the A-B phase, it turns out the only model that reliably predicts neural similarity is BART. And it does so in posterior parietal cortex, the superior parietal lobe and into the parietal sulcus. And then we can move on to the CD phase, which remember, this is where relation comparison comes in. And now we take a different measure. We can take really the same thing we use for analogy, the cosine difference between the AB and the CD, with the assumption that the larger that distance is, kind of the harder it is mentally to figure out that these are actually valid analogies, because the ones I'm looking at are all valid. And what you find is that, again, BART is the only model that really predicts anything, and it's roughly speaking in the frontal parietal region, especially all those frontal regions, which seem to be important for kind of finally putting the analogy problem together. Okay, I see we're coming up on the hour, but I'm like almost finished. I just tell you a little bit about what we're actually actively trying to do now. So, you know, a lot of people could say, well, so far, so interesting maybe, but, you know, what do you got? Proportional analogies, you know, some of my colleagues always say those aren't real analogies at all, and maybe they're right. What about the fancy stuff, the mapping, where you take multiple relations and put them together? So we've started to think about, well, could we sort of go there from what we've done? And recently we developed a simple little analogies of semantic triplets. And so this is the task. So I give you something, we'll call this the source analog, bird, parrot, parakeet, for example. Then over here is the, quote, target analog. And all it is three words. They're actually randomly ordered. You can think for a second, as smart analogy people, you probably are going to figure out that the correct ordering, in fact, we have people drag these guys into boxes, and the correct answer would be vegetable goes to bird. They're both superordinate categories. Lettuce to parrot in the middle category. Romaine to parakeet, the subcategory. And that would be the analogy. Now notice, as I promised from beginning to end today, no verbs, no linking words. Once again, you got to, in Spearman's terms, deduct your own relations, figure out what's going on here, figure out what might be going on here. And notice we tried to capture the kind of asymmetry between source and target. So the source is ordered, that's fixed. But I don't know what the ordering, I don't know whether am I supposed to compare lettuce to vegetable or vegetable to lettuce or neither or what? What are we going to do? And in fact, we're trying several things, and I'm only going to describe what's really kind of conceptually the simplest, although I wouldn't necessarily defend it as the most psychological. But here it is. And it's pretty simple, as you can see, an extension. So we got these three are 3 words in the source. How are we going to represent the entire source? Well, there's 3 relations. Bird is related to parrot somehow, so let BART calculate it. And there it is. We produce its vector. I should say at this point, we've moved from the vector of 79. We've added some relations based on some data from Ben Popoff. We've added the converses. So this version can handle the fact that I don't necessarily know the order of relations because it's got both always by definition. Anyhow, so it's about 250. So that's how big this would be. Parrot to parakeet, well, that's a second relation. And I concatenate it with the first. And if I like, I can compare bird to parakeet as well and add it on as the third relation. So that vector now is the extended relational representation of the entire source, simply the concatenation of individual relations. Then on the target side, of course, things are a little more complicated because basically with 3 alternatives, there are 6 possible orderings of those 3 things. So in fact, by chance alone, you'd only expect to get 1 in 6 completely correct. But in this version of the model, we do kind of the most compulsive thing, namely consider them all, so in Bayesian style. And I've actually put the winner on top, vegetable, lettuce, romaine, and you can kind of see this is highly probable relations, this is very improbable relations, a little more probable again, not so probable. It kind of matches. A near miss actually would flip romaine and lettuce. Then they get really bad. And notice the worst one is backwards, right? To have vegetable be the subordinate and romaine the superordinate is a really bad analogy when calculated this way. So we actually created a dozen of these category style ones. And to generalize a bit, we also created another paradigm such as fin is to fish to ocean. Roughly speaking, the fin is something is part of something and it's located somewhere. So it's like part, whole, place. We took all possible pairs, 12 times 11 equals, I guess, 132 for each of them. And we see what the models and humans do. The human data Nick Ichien just collected like last night over on the right here. This is over 1,000 M-Turkers. And I should say every M-Turker got just 1 example of each of those 2 paradigms. So it only solved 2 problems. So if you think about it, smart humans, if you start to give them multiple ones, they're going to start to learn the paradigms. Because in fact, we're now coming up to the edge of what has been classically thought of as schema induction, where you kind of see the connection. But this is kind of raw analogy. On their very first experience with one of these, how do you do? And the answer is about 75%. Interestingly, the part whole place is a little easier for humans, and certainly for the models. This is word2vec, which notice it's kind of crummy for categories. It's getting respectable actually for part whole place. BART is a little better and fairly close to the human level of sort of 75-ish%. Notice the category 1, of course, has got duplicates 1 relation twice, which needs to be sorted out. Part whole place has 2 distinct types of relations, which are actually easier to sort out. Okay, so let's stop. Just to summarize, to some degree at least, abstract semantic relations can be learned from non-relational inputs, the kind created by current machine learning. We add some smart learning from small data on top of the deep learning from the very big data that created the inputs. And armed with that, the BART system and it can judge typicality and similarity of relation examples, solve simple verbal analogies, predict patterns of similarity in neural responses, and most recently start to find mappings based on multiple relations. So what I would say is, we started with what's kind of a chicken and egg problem, like which comes first, the relations, the analogy, the mapping, and they're all, in the end, of course, they're all intertwined, but the story here, which you can believe or not, is that there isn't actually a chicken. Well, I guess there's an egg. So relations come first. You start from nothing, basically, unstructured stuff. You create some basic relations. And out of that comes analogy, because you can determine the similarity of relations. And when you start to put multiple relations together into these higher order structures, then you can detect similarity of patterns of relations, and you're into something that's more like classically what we thought of as analogical mapping. So sorry to be over time for those who probably aren't here because they had to leave, but for those who don't have to leave yet, I'm happy to take questions.